Well, I think I can start. Not sure if somebody will join, but we are already for the 5 minutes late, so let's start. And 1 second. Yeah, welcome, please. I am starting now, so you didn't miss anything so far. Okay, so here we are. Let's get back to the previous lecture, forcing estimation. You may remember that we talked about wind forces and then wave forces. Before that, we discussed how to estimate wind velocity with probabilities. And we also talked about, and I want just to refresh your mind, we talked about the movement, the six movements that a ship can have because it's a rigid body which can move and rotate along 3 axes. So we have six types of movement. I just want to remind you the terminology. So if we talk about rotation, we call the rotation around the vertical axis yaw, the rotation along the transversal axis pitch, and the rotation along the longitudinal axis, we call it roll. Just also remember the name of the axis. Vertical is very easy. Longitudinal is the axis that is displaced along the length of the ship, and the transversal axis is perpendicular to the longitudinal axis in the other horizontal direction then. And about translations, we call them sway, the translation along the transversal axis, surge, translation along the longitudinal axis, and heave along the vertical axis. Okay, just remember the terminology, and then I want to make a focus on probability, because we already talked about probabilities, and so far I told you that we can assume from a technical point of view that probability is assimilated to frequency. We just mentioned that for some types of probability, or let's say for some types of events, we cannot really estimate probability through frequency. If we look at an event like tossing a coin, certainly we can estimate the probability of an outcome, of a given possible outcome, by estimating the frequency from repeated experiments. But if we talk, for instance, about an election, we cannot estimate the probability of a party or political party to win an election, or a candidate to win an election based on an experiment. It is like estimating your probability of getting the max mark at an exam. You may say it's very likely, I think I have a probability of 90% of getting the max mark, and maybe 80% of getting the laude, but this is not based on an experiment. It's based on your perception, your estimation, your personal guess. And therefore, you understand that this assimilation between frequency and probability works for some type of events, doesn't work for other type of events. And then I think that at this stage we need to better specify what is probability and how we can estimate it. Because when we work with Harbour engineering, there are some type of events for which we can indeed estimate probability based on frequency. And one example is wave height. If I have long-term observations of waves, I can estimate the frequency of the waves exceeding a certain height, and I can then assimilate this frequency to probability. But there are other type of events that we cannot really estimate basing on experiment. And then an example for Harbour engineering is wave probability under climate change. I cannot make an experiment. I need to invent something different. So in order to better understand what are the different situations, the different problems, and the different solutions, at this stage, we need to stick a little bit on definitions. And how to define the probability? This has been a question around which statisticians have discussed for a long time, just because of the examples that I made. So we have a clear perception of what is probability. It's clear for us. So when I say it is likely, so high probability that tomorrow will be a rainy day because I looked at the forecast, we have the perception of what it means, high probability, low probability, etc. But if also scientists, statisticians have to define it, then it becomes a little bit more. So how can we define it? The usual approach today is to define probability based on Kolmogorov's axioms. Kolmogorov was a Russian statistician. He worked in the 1940s. And he was a very brilliant mind. He made a lot of progresses in statistics, but not only statistics, also in mathematics. I'm sure that you heard the name already. And he died relatively recently. I think it was like 1978 when he died. And so he proposed to define probability in a very simple way. And the simple way is by defining axioms. Here there is a link if you want to investigate more. It's on Wikipedia, but let's stick on my webpage. And so I'm not opening the PowerPoint here. I prefer, because this is just a short focus, I prefer to refer here. Okay, so axiom 1, the probability of an event is a real number greater than or equal to 0. So it's a number ranging from 0 to 1, with the extremes included. So the probability that at least one of all the possible outcomes, this is the second axiom, of a process. So the probability that at least one outcome occurs, for instance, if I roll a die, the probability of getting a number as a final result between 1 and 6, including the extremes, is 1. A translation of this axiom is the probability of an event that is certain is 1. Okay? And why it's a translation? Because when I say the probability of getting at least one among all possible outcomes, it means that for sure, whatever experiment that I make, I may have infinite possible outcomes, but the probability of getting at least one of them for sure is 1. So if I say I toss a coin, what is the probability of getting either head or tail? It's of course 1. So you see it's very simple. Axiom 3, this is probably the more technical, but it is very easy. If two events, let's call them A and B, are mutually exclusive, like tossing a coin, A and B are head or tail, then the probability of either A or B occurring is the probability of A occurring plus the probability of B occurring. So example of tossing a coin, the probability of getting either head or tail are probability of head plus probability of tail. So these are very simple, and by your deduction, you can deduce that according to axiom 2 and according also to the other two axioms, the probability of an impossible event is 0. Okay. Now, any way of defining probability, because there are alternative ways, there are other ways, but we assume today that any definition that satisfies the 3 axioms of Kolmogorov is fine. And any way of estimating probability that satisfies the axioms of Kolmogorov is fine. So if I estimate probability through frequency, you see that this method for estimating probability is meeting Kolmogorov's axioms, because frequency clearly satisfies that it's between 0 and 1. Okay, frequency is number of heads by tossing a coin divided by the number of total tosses that I made. It's between 0 and 1, so it satisfies the first axiom. And then frequency, the probability of the frequency of at least one outcome occurring is 1, of course. When I toss a coin, I mean, the number of results divided by the total number of attempts is 1. Good. And also the additive property for mutually exclusive events is satisfied by frequency. So if you estimate probability through frequency, you may get an erroneous estimate. Let's say if you toss the coin 10 times, you may get 4 heads and 6 tails. So you get an estimate for probability of head 0.4 and an estimate of probability of tail 0.6, which is not correct. Fix in your mind this no. It's not correct, but still satisfies Kolmogorov axioms. So frequency is a way of estimating probability that satisfies Kolmogorov axioms. Okay. On the other hand, when I said it's not correct, this means that frequency is not the same thing as probability, because probability is something that it's theoretically valid and should be correct in a way. Frequency, for the examples that I made, is not always correct. Okay, and therefore this proves that what I said, frequency is the same as probability, is not really correct. Okay? Frequency is close to probability, but it's not really probability. When it is frequency getting close to probability, I mentioned to you Pearson, who tossed the coin 24,000 times. He wanted to demonstrate that when the number of attempts tends to infinity, frequency tends to probability. So frequency is a good estimate of probability. It is satisfying the Kolmogorov axioms. It is a good estimate if the number of attempts tends to infinity. Okay. But what if I cannot make an experiment? What if I want to estimate the probability for you of getting, in my exam, 30? Okay. So what you can do is, let's look at the habit of the professor. So what is the range of votes that Montanari gives? So it's between 18 and 30. How many rejections in the past? It's between 18 and 30, or is more concentrated between 25 and 30, with the high frequency of 28. So you make a kind of preliminary estimation, preliminary information by looking at the frequency of my marks in the past, which of course doesn't apply to your case because you may be an exception. Okay? So Montanari may have not given any loud in the past, but you may want to get the loud. So you want, if you estimate based on frequency is 0, your probability. No, it's not 0, because of course you have some chances of getting the loud. So you have to get additional information, like how well I am prepared. I feel I am very perturbed, and therefore, with respect to the usual frequency of Montanari, I suspect that I will be in the upper part of the range. Conversely, yeah, I'm not very well prepared, so let's move in another direction. And there might be additional information besides these two examples, and then you elaborate a kind of expectation. It is the same thing that we do for elections with exit polls and with the preliminary polls. Okay? You see that they are quite good, but sometimes they are plain wrong. And this has been a kind of debate recently, because we assumed, like until 10 years ago, that with the preliminary polls and exit polls, we were really able to predict the outcome from elections. But you may remember last elections, some of the last elections, really the preliminary polls, like 1 week earlier, and exit polls failed. Who knows why? Maybe because there is a reduced attendance at the elections, maybe. So the sample size is, but I don't think so. I think there are probably other determinants. Anyway, you get your guess and then you estimate your probability. Like I think it is, I have a 90% probability with Montanari getting the loud. The important thing is that whatever estimate you make, and this is called Bayesian definition of probability and Bayesian estimation. When you get this name mentioned, Bayes theorem, Bayesian estimation, precisely means what I'm saying now. An estimate of probability based on my expectation, on my guess. But in any case, you have to meet Kolmogorov actions with your estimate. You cannot say, I have 90% of probability of getting the max mark with Montanari and a 20% probability of getting less than 25. This is not possible, okay? The sum must be 100%, cannot be 110. So now you understand what is the basic requirement of probability, and you understand what is the Bayesian definition. There is one thing that we still don't know. Think of an experiment different from tossing a coin or rolling a dice. An experiment where the outcome is a real number. And so, like wave 5 is a real number. Real number means that you never get the same outcome twice, because real number means an infinite number of digits. And therefore, when you observe a wave height, it's impossible that you get an infinite number of temporal digits. So there is never an outcome that is repeated twice. Actually, when you look at the databases, they don't have an infinite number of digits. They may have like 2 digits. If the wave height is in meters, okay, they may have 3 digits, most. So the possibility of getting the same outcome is not 0. It is possible that you get twice the same outcome, but still, you understand with 3 digits, that would be very few outcomes repeated twice, and probably decreasing number of outcomes repeated 3, 4, 5 times. So you understand that the estimation of probability through frequency is not really a good thing, because you get probability close to 0 for any single outcome. And so you realize that you are still missing something, how to define probability for an experiment which may have an infinite number of outcomes. What is the solution? You can guess what is the solution. The solution is like, I'm not interested in the third, fourth, 100 digit. I think it is fine if I estimate the probability of falling into a range. And yes, this is the solution. So, for instance, I may count in the wave heights the probability of getting a wave height between 0.8 meters and 1 meter. And then you get 7 outcomes. So you split a continuous variable, because in this case, the result is, as I said, a real number. You split the continuous variable into discrete outcomes. So basically, you reduce to a finite number the possible outcomes. This is the solution I anticipate, which is fine from a technical point of view, because, as I said, you are not interested in the 10th digit. You are interested in defining an event at discrete time step. So even when we observe temperature, we observe rainfall, it's a real number, the result, but we split them into a discrete set. One thing, when we talk about probability, and I didn't say this before, we refer to probability of events. The events, tossing a coin, waves, extreme wave, rainfall, extreme rainfall. temperature, extreme temperature, heat waves. These are events. The experiment consists in an event. But then, for our ease of tractability, we prefer to describe the result in terms of a number, like tossing a dice, we associate a number. Tossing a coin, we say head or tail. But if we want to make a mathematical representation, it's better to say 0 is head, 1 is tail. So to associate the outcome to a number. This association between the outcome of an experiment and the outcome from an event, the outcome is what we perceive. I get flooded water, okay? This association between the result of an event to a number creates the so-called random variable. A random variable is a number which represents the outcome from a random event. Okay, random means something that is unpredictable. Okay, unpredictable in deterministic terms. Okay, so keep in mind, randomness means lack of predictability. Statistics is called into play when we have some lack of predictability. Predictability means that I can guess in a perfect way the outcome from an experiment, the result, the number. Okay, this is deterministic predictability. When there is some uncertainty, which means that I'm not sure, it means that there is some unknowns, which means limited predictability. This is very clear. I mean, it seems like a naive statement, what I'm just saying now. But actually, it is extremely important to be aware from a technical point of view of what means randomness. What means if I use statistics? It means limited predictability. Okay? It doesn't mean zero predictability. It means that to some extent, there is a limitation to predictability. Okay? Zero means something that I don't have any clue. Okay? Tossing a coin is not zero predictability because I know that it can be a head or tail. I cannot really predict for sure. I toss one coin, I predict if it is head or tail. This is impossible. But still, I can predict that it's head or tail. So in probabilistic terms, I can predict it perfectly. And this is not a useless prediction, really. So if I say that I have a probability of 90% that the max annual wave height is 1 meter, is no more than 1 meter. I say again, if I can say I have a probability of 90% that the max annual wave height in a valley is no more than 1 meter, then it is very useful. It is not perfect predictability. I cannot predict the max wave height, but when I can say with 90% probability is no more than 1 meter, it's a very useful. So don't assume that lack of deterministic predictability means no way. It means that with statistics, we can still derive very useful technical information. And engineers usually, they always work under these conditions, limited predictability. Okay, one more thing. When we talk about probabilities, we can talk of like rolling a dice. I can talk of probability of getting 1, it is 1/6 frequency. Probability of getting 2, probability of getting 3, they are all the same, 1/6. Or I can say probability of getting no more than 3, which means that I have to sum for the additive property the probability of 1, the probability of 2 plus the probability of 3. This is the probability of getting no more than 3 is probability 1 plus probability 2 plus probability 3. Okay? Which is 1/2. Is 1/6 plus 1/6 plus 1/6. It is 3/6, it is 1/2. In the first case, when I talk probability of 1, I'm talking about what we call probability, or if the outcome is a random variable, we will talk about probability density. We will see why. We will see why we change the term with the real numbers. When I talk about probability of no more than 3, we call it cumulative probability. Cumulative probability. Okay, so we can make a difference between probability. Okay? Probability. Between parameters density and cumulative probability. And I made the example of probability of getting randomized 1, 2, 3, which is equal to probability 1 plus probability 2 plus probability 3, which is equal to 1/6 plus 1/6 plus 1/6 equal to 0.5. Okay, this is what I said. Now, what is this? It's a summation for the additive property, for the additive axiom, from the third axiom. It's a summation. So you see that the probability, the cumulative probability, it is given by a summation of the probability of individual events. Okay. Cumulative probability defined in this way, which means probability of no more than 3, if I normalize, is also called probability of not exceedance. Not exceedance. Very good. Now, probability of not exceedance, let's call it PNE, okay? PNE of, PNE of 3. Okay. Of course, I may also define a probability of exceedance. Probability of exceedance, probability of exceedance. Which is, we can call it PE3. And you may ask me, what kind of probability do we use in our engineering calculation? And my answer is, it doesn't matter, because once that you compute the probability of not exceedance, it's very easy because of the additive property. This is equal to 1 minus the probability of not exceedance of 3. In this case, it's 0.5. They are the same, 0.5. So PNE and PE, PNE, sorry. So PNE and PE are complementary to one. Good. Just usually keep in mind that usually we use the probability of not exceedance when we talk about probability of getting away with 1 meter. Not absolute way 1 meter. Usually we don't say it, but it's the probability of not exceedance. Okay? Because it means that if I say probability of getting away with 1 meter is 4.9, it means that 90% don't have just 1 meter. We have all the values between 0 and 1 meter. And this is what we usually use. If people don't say anything, like cumulative probability of 4.9, it means probability of exceedance. Just keep in mind one thing, when you deal with the real numbers, when you deal with the outcomes that are real numbers, you may wonder if, because, very often, probability of not exceedance is expressed in this way. Probability of, let's go the way by x. X less or equal than 1 is equal to. Okay. Now, this not exceedance means that the equivalence 1 is included for the dice. Not exceedance 3 means that 3 is included. With real numbers, doesn't matter if you put the equal or not. Usually also with real number we say less or equal, but equal is never equals. So while we're rolling a dice, it's important to say less or equal than 3 if I want to do 3. If it is a way wide, usually we abbreviate by saying less than 1 or more. And sometimes it's different asking, but then the equivalence is included in the not exceedance or in the exceedance. And I say, with real numbers, from a technical point of view, it doesn't really matter. From a theoretical point of view, it matters when I say not exceedance. A real number, I still have to include the equivalence. Okay. This is what we mean with probability. And just keep in mind that when we say probability, it's something that applies rigorously. When we say frequency, it depends on the sample size. So you have to keep it in mind, because this means that if you want to estimate the probability of wavelength, you have only 2 years of observations, you can estimate the frequency. But you have to keep in mind that it's not a good estimate of probability. This is extremely important because as an engineer, you have always to care about this. And therefore, it's important to see that we understand this definition. So probability is something rigorous. Frequency depends on the sample size. If it is very large, that's fine. If it is limited, then you have to be very careful. Okay. Now we have the problem of estimating it, So it is relatively easy to estimate it if you have a long sample of data. Look, statistics, if you have a lot of data, I mean, it's frequency. It's very easy. It's very, very easy. You don't need theorems or whatever. All the theory of statistics and probability has been devised in order to make sure that when we make an estimate in a Bayesian context or frequentist context, it's a good estimate. Once again, all the theory is aims to make sure that the estimates that we get are good estimates. And then we introduce concepts like bias, central limit theorem, whatever. Once again, have you at the disposal a large sequence of numbers, it wouldn't be a problem. It wouldn't really be a problem. It is very simple. You compute the frequency of your event, and that's it. And you are sure. So this is why, for instance, in climate science, we make paleoclimatic reconstructions, because we want to get an idea, a picture of climate in the past. We don't have numbers, we don't have observations, and then we want to get a picture so that our understanding becomes correct. But actually, very often we have a limited amount of observations, and therefore we have to wonder how can we get a good estimate. And for an engineer, it is essential. It is essential not only for your, I mean, for your career, but just because as an engineer you have a huge responsibility. In some of the cases, if you are busy, if you are involved in a very complex design project, it's like the responsibility of a physician, of the physicians that go in the surgery room, you know. And therefore, you have really to make sure that your estimates are correct. And this is why the theory of probability became so complicated. It became so complicated because, you know, there has been a lot of development to make sure that from a limited set of numbers, we can extract the max of the possible information. And still we have some way to go. And there is also another feature of statistics and probability, which makes it not easily accessible. It is the fact that it's very boring. It is very boring. And one of the reasons that is boring is its complexity. But there is a second reason. The second reason is that it is boring because it applies to generic numbers. It is not really a science that is applied by itself. Statistics becomes more interesting if you refer to waves, you refer to climate change, because you see the application and you see the usefulness. But usually the theory of statistics is made by statisticians, and they address their lectures to a multidisciplinary room of students, and they just make examples with numbers. And this makes statistics in a way boring, not really. Sometimes we feel like there is no real connection with reality. It's the same thing as mathematics. Why it's boring? Because, you know, if I look at the bias trust theorem, Bolzano bias trust theorem, some of the theorems that I remember from analysis 2, analysis 1, you know, they are boring because you don't. Very often we students said, this is really not useful. We don't need it at all. But the reason is that it is like separated by the reality. And actually, as students, we need to apply derivatives and integrals. So it is important that we understand the theory behind it. You know how much differential equations are important to us. And therefore, the ideal thing would be to make a reference to specific cases. Often we discuss this. We professors discuss with the mathematician, try to make examples, but of course they are a multidisciplinary audience. By the way, when I talk about the summation right here, this is an integral, be careful. The integral seems something very complicated. Actually, it's so I said summation because it's discrete numbers. But you can perceive, if you state a bit of a discrete variable, and I need to refer from a continuous variable, infinite of gaps, and here, the summation becomes an integral. And you see that even with a very simple example, analyze you may need integrals, describe likelihood of outcomes. Okay, now, as I said, we have to define probabilities to estimate probability. And let me start with an example. Let's suppose that you have 10 years of wave data, and you are interested in describing the annual maximum failure of 10 years of 10 years of annual max W is the wave height. Okay, so if you get the max of this, max of 10 years of annual maximum, let's call it W star. Okay, what is the probability of W star? It is 1/10. Be careful. 1/10 refers to my experiment. My experiment is 1 meter every year, 1 mass every year. Okay, so when I say 1/10, I have to keep in mind what it means. I have to think of the experiment. The experiment is 1 count every year. So it is useful in technical terms to refer to a more understandable reference, which is the record period. Okay? And the record period is, in this case, T is 10 years. I don't define the record period because I already defined it. But please don't forget the definition of record period because it is something I don't understand why, but students often misunderstand. The record period is the average time between two events, so the same or lower intensity. Okay. The same or, just a second, the same or higher intensity, I'm sorry. Okay. So the record period is the average time between two events which are the same or higher intensity. So if I talk about this W star, the record period of W star is 10%, which means that on average, I wait 10 years before two waves higher than W star are on average, it's even more because there are many people who think that if the record period of W star is 10 years, then once I see W star for 10 years, I am safe. This is absolutely not. Okay? It may pass just 1 year before I see another event with a record period of 10 years. It applies to average. And then in this case, you see that the period of this W star is very 10 years, basically on my estimate. Okay. First, you have to think that this estimation based on frequency is based on your 10 years of data. So to say that W star is a record period of 10 years is basically for the next 10 years, and maybe at a different story. But what if, and this is even more compelling, what if I have to estimate, to get an estimate for, let's see, maybe this in this way, an estimate of W for here one moment. You understand that I cannot get this estimate on the sum of previously. Based on this deep reasoning with I did, it's not possible. And this is why statistics is complicated, because I have to extrapolate information. And this is why statistics has been invented, theory of probability has been invented. And you may think that it's impossible that probability theory probability is a crap. How can I get this estimate based only on the numbers? You may say this is an impossible problem. Actually, if you look at these 10 numbers, how they differ from one another, you can get some information for extrapolating. Like, for instance, if you draw a graph, and you put here your weight line, then you will have the period. So you will have 10. You will get this point here. Instance, and this is W star. But then you can also draw all the other points. Okay, for all the other points, you can get an estimate of the relative period by giving one by 3. So you may get points that are expressed in this way. It depends on your. It depends on the values of W, which is a completely different story if you want points displayed in this way. This one here. And let's assume that this one is the same. And then like this. And then here. It's completely different because what can you do? You know, I look at the probability and I can estimate an analytical function connecting these points. And for the other case, I can also estimate an analytical function connecting these points, which may be something like this. And you see, these analytical functions can be extrapolated. They can interpolate the points. So if I want to get whatever value, whatever value of wave I corresponding to whatever value of reference period. But they can also use to extrapolate. These analytical relationships interpolating individual probabilities are called probability distributions. Probability distribution functions or probability distributions. In this case, I am talking about probability of not exceeding cumulative. Okay, so the shape of this probability distribution is this kind of shape where the relative period, which is more or less, which is derived from probability, is the function is always increasing. It's describing cumulative probability. In fact, I started by talking of probability of not exceedance or exceedance, which is analogous. Okay, it's one the complement of the other. So, probability distributions. You may remember the Gaussian distribution, but let me start from this sketch, which I think it is interesting. It is also easy to be understood. This is an histogram that is derived in this way. The experiment is rolling 2 dice, and then I get the outcome. Okay, so what are the possible outcomes? The possible outcomes are 36. Okay, because if you think of the sum of 2 dice, the sum of the numbers that I get rolling two dice, the possible outcomes are 36. Okay, what is the probability of getting 1 is 0, because the minimum result is 2. What is the probability of getting 2? It is just 2 over 30, sorry, 1 over 36. Because you have only one combination that gives 2, is 1 plus 1. And it is, the probability is then 1 over 36, because the possible combinations are 36. Getting 2, 1 plus 1. You see the graph here? Probability of getting 2 is equal to 1 over 36. Is it clear? And if it is not clear, you may try. It's very easy. You make 10 experiments, and probably 10 experiments you don't get never 2. You get increase the number of experiments, and you will see that the probability is 1 over 36, which is the same probability of getting 12, because it is, you have only one possible combination that gives 12, is 6 plus 6. But let's think of the number 7. The number 7 is given by 6 possible combinations. And these are black dice 1, white dice 6, and then at the opposite, the top of the histogram here, the mouse is on the screen, yes. You see black 6, white 1, but you may also take 5 plus 2, and also 4 plus 3, and then that's the possible combination. So you have 3 possible combinations: 6, 1, 5, 2, 4, 3. But if you switch the order of the dice, then you get 6 possible combinations. And then the probability is 1 over 6. So the most probable result is 7. So if you draw completely this histogram, you will see that first it is symmetric. There is a symmetry in this figure. And then we can describe at this stage the probability with the function. Probability with the function. What is the function describing this probability? It is the Gaussian distribution. So raise your hand if you already know what is the Gaussian distribution or normal distribution. I'm sure that you heard of it already before, okay? You see it is symmetric, and it is bell-shaped. So it is a good function. If you see at this figure here, at these shapes here, they are good candidates for describing, you see here another example. This is Gaussian distribution. They are good candidates to describe, this one. They are good candidates, okay? This is indeed the Gaussian distribution. The Gaussian distribution has an analytical representation that is, here it is. This is the description of the Gaussian distribution. Look, the Gaussian distribution gives, depending on a variable, of course, the figure that you see here is not referred to the example of the 2 dices, because you see that there are negative numbers. It's referred to another example, but it doesn't matter. Just look at the random variable x and probability on the vertical axis. Okay, so the function is this one. You don't have to learn it by memory absolutely. It is a bit complicated. Okay, and you see that the relationship depends on x, the value, for sure, and depends on 2 parameters, because you see that there is, in the right-hand side, 1 over the square root of 2 pi. This is nothing mysterious, but there is a sigma. The sigma is a parameter. And you see the second factor, the second term at the right-hand side, it's an exponential, which is fine. There is x, which is fine. But there is a second symbol, mu, which is another parameter. And in fact, you see in this graph that the analytical, the figure, the shape of the distribution depends on the two parameters. So you see that, for instance, the blue line has mu equals 0, and sigma square is 4.2. And you see that the bell is very peaky, okay? Is thin and peaky. Let's look at the other extreme, the yellow one. The yellow one has mu equal to 0, but sigma square is 5, and it's very fat and not peaky, okay? That's fine. I mean, it means that sigma basically regulates the fatness. The fatness, it's a shape parameter. Shape means fat, thin. What is mu? Mu is a location parameter. You see that the first three equations, the blue, the red, and the yellow, the orange, sorry, the blue, the red, and the orange, they have mu equal to 0. The green one has mu equal -2. And the green one is shifted on the left. Basically, the peak is located in the correspondence of the value of mu. The peak of the distribution is located in correspondence of the value of mu. So mu is called a location parameter. So the Gaussian distribution has two parameters, shape and location parameters. Now, what I was going to say, just a second, because I was saying something of important, but I forgot what I wanted to say. Yeah, okay. Why parameters? What are, first of all, parameters in an analytical relationship? When we talk about an analytical relationship, we can say, we can make a difference between parametric relationship and non-parametric relationships. Okay, I think I can do it in the other. First, let me say something. Why do I insist on these definitions? Okay, I tell you. When I graduated, I had a 5-year course, so it was bachelor plus master. Okay. When I graduated, of course, I got my professional license. I got my subscription to the Harbour, the engineers. The Harbour is the professional, I don't know how to say in English, but the professional association. And so I could start making some design courses. Actually, I started with doing PhD, but PhD was paid really with a low salary, so I was doing some professional work. And also I had to wait until starting the PhD 1 year, so on that 1 year with some professional work. And then I started talking with patients, with my clients, and I was very afraid they were talking in a very relaxed way of terms that I didn't know. And I realized that this is something that makes you sweaty. When you have a conversation with a person, with a client, and you see they are very relaxed and talking with them, and you don't understand. It is really, so I didn't know what meant non-parametric, non-linear. Okay, in professional life, it is unlikely that you get an application talking about non-parametric, but they may talk, for instance, about about names of also of rules which you don't know. Actually, when I started my PhD, it was not clear to me what non-parametric meant and what probability meant, what is, what nonlinear means. So I realized that it's extremely important that it was still that there are some basic terminology which is the most recurrent one. So this is why I'm stressing you on probability, because I could also avoid this. Like, you understand what it means probability, but if you talk, if you happens to be talking to the person that really is used to say recurrent probability, probability of exceedance, probability of exceedance, and you don't know that, so this is why I use this thing. Okay, so now I am talking about parametric relationship or non-parametric relationship. Let me make a simple example of a non-parametric relationships. So let's suppose a y. Let's suppose that I want to make a graph of y along time. Okay. Y may be way wide. So y equal to it's very simple. This is the graph. That's it. There is no flexibility, no way to move from this simple sketch. Okay, now let's look at another one. A very simple one. Y is equal to 2 times t. Good. So this is the result. Okay, more or less. It's a straight line with the inclination. Okay. It passes from the origin. I understand here. If I give values of t, if this is the origin, straight line passes forward from here, then goes up. Definitely. Now let me write a third one. Y is equal to AT, where A is a parameter. So this one can be, it passes on the origin, so it can be this one, can be this one. It can be this one if A is 0. So you see the difference in this case. This is no parametric. This is no parametric because the shape is just one. This is parametric because you can change the value of R. So what makes it parametric is the possibility to change this coefficient, which is the slope. So a parameter is what we define in this way. It's a variable in an analytical relationship, which is not determined, it's not fixed, that can be tuned to allow to change some features of the relationship. Okay. So it's a value, it's a coefficient in a analytical relationship which is not fixed. And therefore which you can change to adapt the relationship. So look at the screen now. You see that E and sigma, if I change them, I have a general shape, or I have a resulting shapes which keep some of the characteristics, like symmetry, like there is another thing that is kept, which I will describe to you in 2 minutes. So there are some features that are conserved, other features that can be adapted. And this is useful because if I have to use a Fourier solution, like I did before here, the relationship between a random variable and an adjective period, I need to look up. I mean, my observations describe a picture. The frequency of my data describes a picture. If I want to write the relationship interpolating this picture, fitting this picture, I need to adapt it. This is why point distributions have parameters. And with these parameters, I can change some of the shapes, some of the behaviors, but not all of them. So in the Gaussian distribution, it's symmetric. I can change mu and sigma, but it is symmetric. You can perceive that the higher the number of the parameters, the higher the flexibility. And you can perceive that they may have different relationships, candidate relationships. There is not only the Gaussian distribution. If you heard, you know that there is also the Gaussian distribution, which is not symmetric, two parameters. Because you remember, the Gaussian distribution, two parameters, and it's not symmetric. So this is why we need a theory of probability. This is why we need several probability distributions. Because depending on the problem they have, the fitting changes is different. So the Gaussian distribution is a possibility. There are other possibilities. Actually, the Gaussian distribution is not very handy. It's not very useful for symmetry. It's not a behavioral nature. If you look at your weight data, why did you use the Gaussian distribution? Because the probability are also symmetric. So the figure that results in the screen of the Gaussian distribution, is not this one. Probably the Gaussian distribution that you study describes the cumulative probability. What you see on the screen here is probability, not. Okay, because it refers, we remember the example of the two dices. We describe the probability of getting 7, not the probability of getting no more than 7. So this figure that you see on the screen describes probability. The Gaussian distribution is probability of noise or probability of receiving, depending on how the question presented to you. But it's very likely that she presented it to you in terms of probability of not symptoms. Okay, so moral of the story, this is not very useful because our processes in nature are often non-Gaussian, but the Gaussian distribution is very fine because is an interesting property in statistics, which is, I think it is fascinating, or more than interesting, it's fascinating. Let me describe it. I think here I can clean the blackboard. What is this interesting property? It is summarized by a theorem which is called, and I really invite you, if you want to try to get some interest, some passion in probability, you may have a look at the Wikipedia page of this theory. It is extremely interesting. The central limit theory. What does it say? The central limit theory says that whatever phenomena you are studying, so whatever random variable you are studying, if you take the average of your random variable over a very huge time, so you make an experiment in vector, and then you take the average on a very long cycle of this outcome. Let's suppose that you generate 1 million data through an experiment, 1 million, and you take 1,000 averages over 1,000 numbers. So what you do is I take the first 1,000 numbers, compute average. And then I take the second 1,000, compute average. Third 1,000, I compute average. So for increasing the sample size, for increasing the size from 1,000 to maybe 2,000, 3,000, the average is computed for 3,000, then the results asymptotically, so for sample size that to infinity, the results are described by the Gaussian distribution. So the Gaussian distribution is a limiting distribution where you average over increasing sample size, which means that whatever you are describing, the number of potatoes produced in a 1 hectare field, the weight height, and whatever, the number of cars passing every day in the highway, whatever. If you average along several results, you get numbers that are described, still random numbers described by the Gaussian distribution. Which means what? Which means that in randomness, there are rules, which it is clear, it is obvious, because if you think about randomness, of course there are rules. I mean, we see these rules in everything, in medicine, in tossing coins, whatever. But the fact that these rules are so rigorous, it is really interesting because it shows that studying randomness is very useful. Actually, even when we describe events with a limited sample size, we don't have so many data. And also, we are very often interested in point values, not long-term averages. So we don't use a lot of the Gaussian distribution for this very reason. Because we don't have many data, and we are interested very often in not in the long-term average. But if you describe data like water resources management over long time steps, then the Gaussian distribution may be useful. One thing which is preserved not only by the Gaussian distribution, but by any probability distribution. Look at here. If you sum all the probabilities that you see on the vertical axis, so these probabilities are let's say 6 over 36, 5 over 36, 4. Let's take the sum. 6 plus 5 is 11, plus 4 is 15, plus 3 is 18, plus 2 is 20, plus 1 is 21. Just 1 second, because there is something that I'm missing here. Because what I was saying, and then let's see, because why the sum doesn't sum to what I'm saying now. The sum of these probabilities over all the possible outcomes must be 1. There must be 1. So, which means that the integral of the probability distribution, remember I'm talking about probability distribution, not cumulative probability. The integral of the probability distribution must be 1, because the integral means that I take the sum of the probability of all the possible outcomes. Now, let's try to make the summation again. Let me see, because I think there is something. Yes, now I am okay. Let me compute the sum again. It's 6 plus 5, 11, 15, 18. Yeah, okay. 1 over 36 has to be multiplied by 2. And so it is 2 over 36, because there is 1 on the right, 1 over 36, and 1 for 12, and 1 for 2. So this is 2 over 36. This has to be multiplied by 2 as well. So it is 4 plus 2, 6 over 36. This has to be multiplied by 2 as well. So it is 6, 9, 12. Again by 2, 12, 16, 20. And then again by 2, 20, 25, 30 plus 6 is 36. So you see that the integral, the summation of all the probabilities must be 1. And this is a common feature of all the distribution. So if you look once again here to the Gaussian, here, the integral, the area that is below the curve is 1. Indeed, if you look at this picture here, look at the base of, look at the blue line. The blue line has a base of more or less 2, less than 2, let's say 1.5, and an height of 0.8. So 0.8, 1.5 is a little bit more than 1, because my estimate of 1.5 is not correct. So the average here is about a little bit more than 1, the average width of the distribution. And for a height of 0.85 and a width of a little bit more than 1, the area is 1. And this, which means that if you increase the fatness, then you have to lower the peak, which is what happens here. Okay. Now, there is one last thing that I want to tell you, and then we can make the break, about probability. And let me just check, it is here. So, it is the issue of the real number. I said, let's divide in discrete steps. And let's compute the probability of the variable of the real number to fall within each of these discrete set. So, and this is what is written here. Let's see if I can. Okay. So let's suppose that which I put on the horizontal axis. Usually the random variable is put in the horizontal axis in the graphic rate distributions. And let's suppose that I want to estimate, I want to use the same symbols. Okay, so this is X. And here we use this symbol, capital X. Usually in statistics, what we do is to indicate a random. So if I say I want to indicate the way back with W, so I use capital W. A specific outcome, use the lowercase. So a precise value of X, of the random variable capital X, is indicated in the lowercase. This is a conventional statistics. Okay, so this is capital X, and this is a specific value. And then I said, okay, let me define a range around X. And the range has a bit delta X on the left and delta X to the right. And this delta is arbitrary, okay? I take an arbitrary size of the range. And then this is X minus delta X, and this is X plus delta X. Very good. And now I compute the probability through the frequency of the outcome from within here, which is given precisely by this equation there, where I indicate the frequency with F. So FR X minus delta X, and then here I use the okay, semicolon. x plus delta x. And this is equal to the number of times that the variable falls within the range divided by the total number of the experiments. So that's and x, which means the number of times they got a variable within the range divided by the total number of attempts of experiments that they made. Okay. This is the frequency. Okay, good, but you understand that this frequency of cancer depends on delta x, depends on the size of the range, which is not very good. I mean, if I want to estimate a probability value for a given outcome, x in this case, it must be something that is not subjective. Okay. First of all, just remember that what I'm describing here is the probability of getting a discrete outcome. So I have a discrete number of outcomes. So I have a situation which is more similar to rolling a dice. I believe that I split the range of the random variable from a real range to a discrete set, a discrete group of ranges. But once again, the most important problem here is that the estimate of the probability cannot be subjective. So, how can I make this definition independent of delta x? So, how can I make this definition of probability objective? The idea then is to define the probability as frequency of this one, repeated, divided by delta x. This is the idea, which is sensible. It's a good idea because with increasing the size of the range, we're getting more numbers. If I divide by the size of the range, which is increasing as well, then I can get something more objective. Something that becomes more appealing. This is what is called probability density. Why density? Well, you understand why. Because it is divided by the frequency, it's divided by a range of the random variables. So it's not describing, strictly speaking, a probability, it's describing a density of probability. It's describing probability per unit random variable. This sensible probability density. And usually, this is lowercase. Lowercase. So we use usually capital letters or typically capital P to identify the probability of extinction, so cumulative probability. And lowercase p to identify probability density. So the equation, and then we make our graph of the Gaussian distribution that you see on the screen. This is not the equation of the Gaussian distribution. This is still the equation of the probability density that I defined there. Here on the screen, I'm using the letter F to define the probability, or better, the frequency. On the blackboard, I used P. It doesn't matter. The important thing, you see that it's lowercase even here. So again, if you look at the relationship of the Gaussian distribution, this is lowercase. It is described with the probability test. A final distribution will make a break. This step on probability density is what made, at least for me, understanding probability is complicated. Actually, it is a very simple step. So I tried when I started teaching to make this step very simple. If you look at over the probability books, usually the rest is defined in a different way, which I found not so exciting. I tell you later how it is defined because it's very simple, but I don't want to tell it now. And we say it now. And as I said, I found this step between the probability to define the probability density the most complicated thing to understand. And actually, it is simple, but my suggestion for you, try just to dedicate a bit of time, not too long, to understand this step, probability density, probability, relative probability, just make an attempt to clarify in mind what is the meaning. And just start from the consideration that we needed a way to deal with probability of random numbers, of random real numbers. Random real numbers. And this is why I find it probability density. Okay. If our outcome was independent of was discrete, always discrete, wouldn't introduce the probability density. Still, it is useful because I'll tell you later why. Do you have any question? Okay, good. Let's make a 15 minutes break. Then we make an exercise in the second part. Yeah, after 5 minutes, closure of this dismissal of the probability. Okay, see you at 3:05. Let me see what, sorry. I removed the part of the video with the break last week. Okay. Unfortunately, today there is a strike of the trains, so I checked that I need, unfortunately, several trains were cancelled. I need to close the lecture at 4:05, more or less. So in 1 hour from now. Just wanted to let you know because otherwise they will get in trouble. And if there is the need to recover some of the time, we will find the way. We are supposed to close our lectures on April 16, and maybe that I can teach some time more the same day or April 9, we will see. Okay. Good. As I mentioned earlier, I would like to make an exercise, but before I move to the problem, which I want to discuss with you, let's say one final thing. Given this definition of the probability density, there is an important property which I want to highlight, which I already mentioned. And it's the relationship between the probability and the cumulative probability. I already said that the cumulative probability, which is a probability of not scalars, defined as the probability of not scalars for the purpose of this discussion, is given by the sum of the probability of the individual outcomes. So I said, for instance, that the probability of this is given by 1 plus 1 3. I want to extend this analogy between the cumulative probability and probability to the case of probability density, because of course there must be a relationship between probability density and cumulative probability. So if I indicate with the probability of capital probability capital P of X, the probability of not winners of a given value of X, like this one, this is given by the individual probability of the lower ranges which have to be summed. So if I want to get the probability of X equals to X, I have to get the probability, the sum of the probability of X falling into this range plus the probability of X falling into the previous range, etc. I have to take the summation of the probability of the individual outcomes. But here I'm dealing with the probability density. So I have to take into account that probability is not the same thing as probability density. Density is obtained by dividing by the times. So the summation can be expressed in terms of an integral because I have infinite outcomes when X is a real number. Integral, for instance, between minus infinity if the range of the random variable is also the range of the negative numbers up to lowercase x of what? Of lowercase p and of tau. But this is probability density. So in order to get the probability, I have to multiply by the x. This is the relationship between probability of not exceedance and probability x. That's it. Now, when I told you that in the probability books, the probability density is defined in a different way, what they do actually is to define first the creative probability of not exceedance, which is easy. Because even for a real variable, it is easy to say what is the probability for value to be lower or equal than 20, lower or equal than 30. So they define the cumulative probability first, and then they define the probability density as the derivative of the cumulative. So what they say is lowercase p of x is equal to the derivative of capital P x in the x. This is what they do. it's perfectly fine. It's probably more 17, let's say. Given that it's a real variable, we can access a real variable, we can take the derivative. And I prefer to start from the definition of probability density and then define the cumulative probability as the integral of the place. I think this is more than what you need. If you, in a way, became quite confident with these definitions, in your mind, you have to clear what is probability, what is probability of examples, what is probability density. So, what is probability of rolling a dice and getting one? What is probability of rolling a dice and taking no more than 3, which is cumulative probability or probability of examples? If you become confident with probability density of wave height, does it mean? So probability density of wave height in 1 meter, very well. This is all what you need to know. And then you just need to know that there are several probability distributions that can describe these densities, cumulative probability, and just take into account that this is the Gaussian distribution, which is defined in, just as an example, is defined in terms of density. Why? Because like any other mathematical relationships, there are some probability distributions, some probability relationships which can be integrated analytically, others that cannot. The Gaussian distribution, there is no analytical expression for the cumulative probability. This relationship that you see on the screen cannot be integrated analytically. You can do it numerically. Good. Now, I think we can now, do you have any question, any kind of concern, doubt? Okay. So I think we can turn to a couple of exercises. First, a very simple in R. You already know what R is. Very simple numerical demonstration of what probability is can be computed into R, because I think it helps. Okay, this is our console. Let me just increase the font. Okay, good. And let me clear the screen. Okay, once again, we are learning by doing. So try to follow me either with the PC, you can repeat it, or your tablet, or just looking at the screen. And let's suppose that we have some wave data available. In order not to lose time to find a wave database, let me generate artificial numbers, okay? And into R, you can generate random numbers. The way to generate it is such that you have to specify how many numbers you want to generate. We can take 1,000. And you have to specify the probability distribution, because if it is a random generation, you have to specify the probability distribution. Let's take for simplicity the Gaussian distribution, because this is just a numerical example, okay? And then the instruction is this one. Let's call it wave D, wave data, is equal to, the function is R norm. Norm stands for Gaussian. R stands for random generation. And then I have to give as parameters 1,000, the number of data I want to generate, and the value of the two parameters. Let's put 0, 1. 0 stands for mu, the location parameter. 1 stands for the sigma. Let's make a plot just to see how it behaves. Plot wave D, and let me make the plot with a line, not points, because points, it's a random, it's a mess. Okay, this is my generated data set. You may have downloaded it from a database. Look, this is a random Gaussian distribution with location parameter 0. So you see some negative numbers because the Gaussian distribution, remember, is symmetric. So if I put the peak of the Gaussian distribution at 0, it means that I have also negative values. Of course, with wave data, in principle, you shouldn't have negative values. But sometimes you see standardized data in the databases, which means that they want the data to have an average of 0. So you may get some negative values. But in any case, for our exercise, it doesn't matter. So we may want to see how it behaves, the probability distribution of this data. And then, in order to do that, we can just apply this computation. We can split the data into set of discrete time steps. And then we compute the frequency in each time step, how many data are flowing into the current rate, sorry, for each step of X, how many data are flowing into the step, and then divide by the length of the step, get the frequency. Is it clear what I want to do? So I take the range of the data, split the range in steps, discrete steps, and I count the number of data flowing into each step, divide by n1000, divide by x, and then the result against x. It's not particularly difficult. Okay? If you had to do that in Excel, it would be a bit, in R, it's not so difficult. Okay, so let me just think, because I am elaborating it just on the fly, okay? Let me just think. First of all, let me compute the range of the data. So min of wave D and max of wave D. The max I expect is 3 something, because it's symmetric. You see? You see the symmetry? Okay, fine. Now, let me think of an easy way to do that. Okay, first of all, let me define the vector P. First of all, I have to decide how many steps I want to get. Let's say 50, okay? So n equal 50. This is the number of steps between -3 and +3, between -3.2 and +3.6. I want to divide in 50 steps. Okay, n equal 50. So what is the delta x? So the dimension of each step. Okay, let's write delta x is equal to min or max, let's say max wave D minus min wave D. Okay, you have to close another parenthesis divided by n. What is the result? Delta x is 0.13. Is it clear? What I computed is the range, and then I divide it by 50, and I get the delta. Good. Now, in each one of these deltas, just not one thing before I move forward. The delta I define here is actually twice the delta I define. Because here I want to show what the price on the left and the price on the right. Actually, what I can do here is the overall size of the step. Just beware of the fact that there is this difference. Okay, now I have to make 50 computations. In each of these steps, I have to count the number of data. Okay, good. So let me think how I can do that. So first of all, I have to make 50 computations. So I need to write a cycle. You have some experience in coding. You know what is a cycle. It is a computation that has to be repeated an assigned number of times. So for 50 times, I have to compute the number of data that fall into each step. So I need a cycle. The cycle in R is written in this way: for cycle variable I, this is the variable that at each time step is increased one. Okay? I in 150. You see, now R is waiting for an input. R wants to know what is the instruction that has to be repeated 50 times. Everything clear so far? Okay, given that the instruction is more than, well, yeah, please. Yes, is the min of the minimum value, min wave D is the minimum value of the number I generated. So look at the plot. You see that the minimum is -3 and the max is +3. By 50. N is 50. You see that I defined N equal to 50 up there. Okay. N is the number of the total number of steps. And the total number of data is 1000, which was defined first instruction 1000. And let me just interrupt the cycle here. Sorry. Yes, okay. You can also estimate the number of data in this way. Length, sorry, wave D. And the number of steps is different. It's something that I fixed. Okay, N is fixed by me, 50 steps. Because I want small steps, but not too small, because otherwise the number of data falling in each range, in each sub-range would be too low. I see that you are still in doubt, so what is your doubt? We are considering a lot of wave height observations. So it's not a single wave. It is 1000 data of wave height have been collected in 10 years. Okay. Like every day you observe a wave height, the maximum of the day, and then 1000 you need 3 years. And then you get 1000 observations, and I split the range covered by the observation from here to here in 50 parts. Because as you see there, this is the entire observation axis. I need to split the range in single steps. Yeah. I mean, of course, it looks easy to me, but because I did it, and if you have to follow, it's not. So if you have some doubts, just feel free to say. Okay.
We are looking at the each axis. In our data, we are looking at each analysis.
Yeah, if you look at this graph here, this is a plot of the data, and they are on the y-axis. Usually, when you look at the probability distribution, they are depicted by putting the data on the horizontal axis. Okay, because if you look, for instance, here, you see that here, the Gaussian distribution, this is the variable, capital X, it's on the horizontal axis, and you put probabilities on the vertical axis, because it's a different type of graph, you know. In this graph here, you have like numbers over time. In the other graph, you have numbers and corresponding probabilities. So the numbers are the independent variable. So usually we put on the horizontal axis the independent variable. In this case, the independent variable is time, and the dependent variable is wave data. And then when you pass to probability, you compute the probability based on the wave data, which become the independent variable. Okay, other questions? Okay, so let me repeat the cycle because I deleted it. Okay, for I in 150, now I need a curly bracket, and just 1 second because I don't remember. Yeah, here it is. Why a curly bracket? Because I have more than one instruction to give. Okay, so now I have to compute for each sub-range, each delta x, the number of wave data that are falling there. Okay, so just here. Let me draw my horizontal axis. This is my delta x. This is my capital X. And here I start from minus 3.2 something. And the upper limit of the range is plus 3.6. Now I have to convert the first step, and this is my delta x. I have to look at that range, minus 3.2, and this is something like minus 3.7. Because remember, my delta x is about 4.13, we computed it earlier. It's okay. And then, in this range, I have to count number of x to a new value. This for the first step, and then I have to make it 50 times. Good. Now, let's compute then the probability density, P equal to. First of all, I need to know the number of data falling into the step. So P is equal to, okay, length of what? Of wave D. And then I have to put the condition. The length of wave D, the total length is 1000. I am interested in the length of wave D falling into the range minus 3.2 minus 307. So wave D, and here I have to put the condition. So wave D greater than minimum wave D plus okay, let me open a parenthesis, plus delta x times I minus 1 . One second, okay, let me put a parenthesis here. So let's see what I have written. I have put a condition. I want to know the length of the vector wave D subjected to two conditions. The first condition is wave D must be greater than the minimum plus delta x times I minus 1. Look, when I equal 1, the result of this operation is minimum wave D plus delta x times 0. So it's just minimum of wave D. But the next step, it will look at the next interval. Okay, let me just complete this. And then second condition, wave D greater, wave D lower than min wave D, okay, plus delta x times I. Okay, I close this. I need to close the other one. I need to close this and this. So I hope I closed all the parentheses. So you see length of this vector subjected to two conditions, wave D greater than its minimum plus delta x times I minus 1. Second conditions, wave D lower than its minimum plus delta x times I. In this way, it explores the whole range step by step. Of course, I may have made some mistakes, like forgetting a parenthesis, or I'm not sure if the two conditions have to be put together in this way. Let's see, okay? And then I can close it. No, sorry. Now, for sure, it doesn't work. Why? Because I made at least one mistake. I forgot to define P. Given that P is going to be a vector, I need to define it. So if I press return, indeed there is an error. So first, let me define the vector. P is equal to repetition 050. And this is defined. And then let me repeat the cycle and let's eliminate this error. Let me just check because I don't understand what is the mistake that I made here. Length, wave D, okay, wave D. So here I opened one round parenthesis, second round parenthesis, third round parenthesis, 2, 3, 4, 1, 2, 3. It looks like it's okay. Let me just see. So here it's 1, 2, 1, 2. Okay. 1, 2, 1, 2, 1. Okay, there are too many parentheses. Just 1 second. 1, 2, 3, 2, 3. One, 2, 3, 2, 3, 4. Okay, 1, 2, 3. Okay, this is correct. Here it's 1, 2, 1, 2, 1, 0. Oh, it looks okay. Okay, let me just check because I think the mistake is still there. Okay, so just let me just make a sequence of attempt. When I get these mistakes, I try to explore by trial and error what is the problem. Let me see if the problem is that I put, yeah, it looks like I just needed to put a and not two ends. Let me see what is the P. No, P is 0. So there is some. Yeah, correct. 1 second. Now I am ready, I hope, to repeat it correctly. 4. I think I just need, I can leave out the parentheses. I forgot to put the index I in P. Let me see, P. Okay, good. So these are the number of observations falling into each step. And if I compute the sum of P, it should be 1000. Okay, I think the reason is that I'm missing one step here, because I think if I divide by 50, the steps are probably 51. Anyway, it's okay. Okay. Now I can plot these numbers just to see what is the look. Okay, so plot P type equal line. You see that it's similar to the Gaussian distribution, more or less. Why it is so scattered is not regular, because 1000 is too small. If you have doubt here, the only doubt that you may have is in this instruction. So let me just try to repeat it, what this is doing. This is computing. So, and we yeah, okay, and then and here, okay, and so forth. Because I start from the beginning, and I have one data, but the data has to be multiplied by the cycle value, because each cycle is new data through. So if you look at the screen, is length of wave D, but has to be subjected to two conditions. First, it has to be greater than this and lower than this. And the second step, wave D has to be greater than this and lower than this. Okay. So you see length of wave D, and then the two conditions between the square bracket, wave D greater than the minimum plus 1 delta x, 2 delta x, 3 delta x, and wave D lower than minimum plus 2 delta x, 3 delta x, etc. Is it clear? There is one thing that I want to make, which is, I want to repeat it. Let me just make an experiment with 51 steps. And then sum P. Okay, now we are getting close. So, yeah, okay, I understand why I am missing. You know, I am missing two variables, because when I took the sum, it was 998. Why? I tell you why. Oops. Let me just stick on 50. The reason why I'm missing two numbers is that I need an equal here. Okay, just 1 second. Still missing one. Okay. Anyway, I improved. Let me just try again. Okay. This is the correct one. I'm still missing one, and because no, now it's okay, perfect. Don't understand what I made it wrong first. So let me just repeat it. Now I included everything. The reason is that for the lowest and the highest value, I need to put the equal, because otherwise it is excluding it. And this is the resulting graph. As I said, it is smoothed because the sample size 1000 is small. But these are not probabilities, because you see, this is the number of times. Now I have to get the probabilities. So let me just repeat it. This is my P. Now I have to divide by 1000 and to divide by delta X. And now I should have the probabilities. Let's see, plot. Okay, here is the plot. These are the probabilities. Let me just check. Yeah, more or less should be like this. And let's see the integral, sum of P. Integral of probabilities should be 1. No, it's too much. So let me just repeat it. It's 1000. Okay, that's perfect. And okay, yeah, sorry. I made a mistake here in the integral. The integral is sum P times delta X. The integral is has to include the X. It's 1/13, this is fine, because there is an approximation, you know. The approximation is 1/13 is fine. Now, is it true that if I increase the sample size, it becomes more similar to a Gaussian distribution? Let's try. Now let's take a sample size of 1 million. One second, okay. Let's add 3 zeros, 1 million. And then we can compute again our probabilities. First, let's see the sum of P. Yeah, sum of P times delta X. Still, it's not correct. Okay, now let me look at the graph, and then we explore why. Okay, first of all, it is more smoothed. There is something that it is not clear to me in the yeah, okay, just 1 second. Plot P. Plot P. Let's see, plot P X and delta wave D. Okay. Let me just look at this plot and let me just repeat the, okay, R norm. This is perfect. Okay, mean wave D. I just want to check if the generation of random number was okay. Max should be something around 4. Very good. Yeah, I understand what I made wrong. And then let me repeat here the computation. And okay, here I have to divide by 1 million. Okay, now sum P should be around 1. Still is 8, but let me just see the plot. I think I forgot something in plot. Oops. Okay. Okay, here there is a problem with the generation of random numbers. Anyway, it's fairly okay. There is a problem with the last number, which we need to solve. But before I move forward, the computation is now done according to an algorithm that I'm writing on the fly. So there is some imprecision that I still need to correct. Let's say that at least it works with the random generation of 1000. Let me repeat it, and then I can compute it again. Sum P. Just 1 second. This is 1000. Okay, good. Sum P. Perfect. Now it's 1, and let me make the plot. And here is still P type P. Just let me check. I don't understand why, because it looks correct in terms of number, but the plot it doesn't work. Okay, anyway, this is an algorithm that I tried to write on the fly. So, you know, we need to check what's wrong. But what I wanted to say is that after I generated the numbers, there is an R function which allows me to compute the probability density in just one instruction. And this function is density. Density wave D type equal line. So let me just show this before I move forward by trying. And this is the density estimated by R with its function, which is fine. It is fine. Still, you see that it is irregular. Keep in mind that R, when computing the frequency, uses my same method, dividing the range in 50 steps, but the results are smoothed. Smoothed means that they try to eliminate the irregularities by smoothing the curve. So this is why this curve is more precise with respect to the previous one that I generated. So let's now try with 1 million, okay? 1 million. And then density again. You see, it is much more regular. This is estimated by R, okay? Still, my algorithm had some problems. Let me try to make just one attempt to solve it, because it worked the first time, it must work also in the other. Let me just simplify. Divided by 1 million. Okay, the delta X has not been recomputed. This is the problem. The delta X needs to be recomputed. So if I keep this delta X in this form, let's just see. In weight D, max weight D, because anytime that I generate random numbers, the range changes, and also the delta X has to be changed. Minus mean weight D. Okay, good. Divided by 50. So this is times 50. Let's see. I'm not sure it works. Be patient, because, you know, on the fly is not easy. I don't think it works. But anyway, doesn't work. Anyway, you can try. It's a useful exercise if you want to try to correct it. And I also will try, and maybe next time we can converge. Let me see what time is it. And okay, we have 10 minutes. I'm sure this example, if you try to repeat it, it is useful. Okay. Now, next step. Let's make an exercise which is more related to our task. And in particular, if you look at our web page of tutorials, there is an exercise here, computation of wind actions on a moored ship and computation of mooring forces. Let's have a look at it, because this is an exercise which is more of the kind of a lecture. One important thing, this exercise, I think it is useful, like the one that I did earlier. If you try to repeat it, it's for sure it is useful. On the other hand, it's not something that will be asked at the exam, just to make it clear. Okay, so this exercise, it looks like a lecture. There are indeed also some informations that are given here, which are not given in theory, but anything that is related to this exercise will not be a subject of any question at the exam, just to be clear. Also, because you will see that the information, I think it is interesting, the additional information that is given here, but it is something that if one wants to learn it, has to be learned by memory, which is not really what we want to do. So let's look at this exercise. We just try to have a look at the text because unfortunately I have only 10 minutes. So a ship with a displacement of 3,300 tons, a waterline length of 117 meters, so it's quite a huge ship, a draft of 5 meters, a beam of 12 meters, pivot point, stational point, located at 55 meters from stern. So I start from the stern, the rear part of the boat, and I go along the boat for 55 meters, and I get to the pivot point. A windage area of 950 meters. So these are the data for the ship. Okay. The ship is moored to a berth with 6 mooring lines displaced as in the figure that we will see. It is down here. But we have only to look at the red lines. Okay, the yellow lines are just given to provide you with a picture of the complete mooring lines that would be needed to keep this ship safely berthed. If you had only the red ones, it wouldn't be safely berthed. The reason why here in the exercise we are only considering the red ones is simplicity, but I also wanted to show the yellow ones. So red lines, the yellow lines are additional ones that are shown for the sake of illustrating, okay? The ship is subjected to a wind velocity of 50 knots, 92 kilometers per hour. It's a huge wind, with wind direction perpendicular to the longitudinal axis. So it is, the wind is in the transverse direction. It's the worst possible condition for the mooring lines, okay? The ship is moored with mooring lines whose behaviors are given here. So each mooring line is composed by 3 ropes. This is what usually happens. We use a set of ropes. We put together like 6 individual ropes to make a single mooring line. If you look in the ports, in the harbors, at the mooring lines, they are huge ropes which are composed by putting together individual ropes. Each rope has a cross-sectional area of 30 square centimeters. The elastic modulus of each rope is 125 kilonewtons per square centimeter, and the breaking tension is 25 kilonewton. Why we are given the elastic modulus? Because the ships are moored with elastic mooring lines, and the reason why they are elastic is clear, because we want to dissipate the strength. On the other hand, if the ship is moored with elastic lines, in the computation of individual mooring forces, we need to take into account elasticity, clearly, because elasticity allows the ship to move, and therefore the strength, the forcing on each mooring line is adjusted by elasticity. So you understand that it's also a problem of structural mechanics, you know. Now, what is our task? Computing the wind force and the yaw moment. The yaw is the rotation along the vertical axis. And we need the yaw moment because if we want to estimate the mooring forces, we need to put together the drift and the rotational moment. The drift is the action of the wind along the wind direction. But then we have to add the rotational moment given by the fact that, remember, the center of gravity of the windage area is not on the same vertical line as the center of gravity of the submerged part of the boat, sorry. So basically the pivot point is different is located on another vertical direction with respect to the center of gravity of the windage area. Okay, so this is my sheet. This is the base. So the center of gravity of the system is of here. Of the sorry, of the sea, of the underwater part of the world is here. And the center of gravity of the windage area is here. So basically, the main force is applied here. Therefore, we can looking at the board of the top, everything that's fine. Also, reinforcing the resulting reinforce from the sphere, this is the excess field respect to the point side of the here shown. Okay, so we have to compute the wind force and the yaw moment, and then we have to compute the mooring forces. The mooring forces, to compute them, I need the full coordinates of the bollards, of the bits. So the bollards are the extreme of the mooring lines over the berths. The bits are the extreme of the mooring line over the boat. I don't need the coordinates of the bits. What I need is the coordinates of the chocks. The chocks are the holes in the boat through which the mooring line passes through. And also I need to know the total length of the mooring line. So just 1 second, chocks are chocks. 1 second, because I think I have a link to a figure of a chock. No? choke boat. Okay, this is a choke, like this one. You see the mooring line passes by this. So I need the coordinates of the bollard and the chocks, and then the total length of the mooring line. So here I have the coordinates of the bollards. I have 6 mooring lines, so 6 bollards, 6 chocks. Okay, and then there is additional data that are given, like the wind coefficient, 1.3, direction of the mooring line on the vertical axis, they are horizontal. For simplicity, they are taken to be horizontal. And then we assume that the mooring lines are 50% longer from bitts to bollards than the distance between bollards and chocks. The distance between bollards and chocks can be computed by the coordinates. And then the total length, I increase 50%, 15, sorry. Now, compute the wind force is relatively easy. I have to apply the relationship which we studied last week by taking these data for the wind velocity, wind edge area, and the angle of the wind with the ship center line, which is 90 degrees. So this is relatively easy. What is definitely more difficult, and we will discuss it next Wednesday, is to compute the resultant forcing along each mooring line. We have a R code already prepared, available here, from which that we can use to make the full computation. But we need to discuss how to make this computation. It is easy for the resulting wind forcing. It is easy also for the yaw moment, the rotational moment. It's not so easy for the structural mechanics problem of decomposing the wind forcing and the rotational moment along the direction of each mooring line. Unfortunately, as I said today, I have to stop here. Next week, I will start with this exercise. Before then this, I will provide you with the corrected on-the-fly code that I tried to make today. It would be a useful exercise for you to try, you have the video, to try to yourself and make the code. Up to you. Questions? Thank you.